C class. We had started with gravitational potential. Till now also Abir was trying to join. Abir couldn't join. Ali, Alina and Jaslina there. So I think I've waited for 10 minutes. It's a long time. Now I have to start with the class. Let other students join late, whatever. So see, 4-point masses are placed at the corners, means vertices of a pentagon. Pentagon means it has 5 sides. And you have to find the field at the center. So let's say this is A, this is B, this is C, this is D, this is E. And you're calculating the separation from this. You require this, you need this, you need this, and you need this, okay? Now, we have to calculate the gravitational potential. It says 4-point masses are present. So C class, 1-point mass is present here, 1-point mass is present here, 1-point mass is present here, and 1-point mass is present. But there is no point mass present at this point C, right? Because 4 were only there and there are 5 corners of pentagon. For pentagon, you have 5 vertices. So how are you going to solve this question? See, if these all 4 were present, that at the center, what would have been the gravitational field? I think I've discussed this with you, that if all were there, let's say IA plus IB plus IC plus ID plus IE, if all were there, so then this would have been a symmetrical figure if this 5th point mass was also present. If 5th was also there, then this would have been the case, and at the center it would have been 0 if it was symmetrical. Right? If it was symmetrical, then this would have been the case. Now, what is IC then? IC is going to be, if we say magnitude of IC, it is going to be IA plus IB plus IC plus ID, this magnitude. Because right now this is asymmetrical. This is asymmetrical. So what do we have? We have this point C missing. So what is the best method that you have to solve these kinds of questions? In class 12th also, there are various questions where you have to find out the value of the final point where the other 4 are given. It will provide you rectangle and it will give you just 3 masses. So same method you have to apply. You will assume that if the 5th was there, then at the center it would have been 0. So if this is not there, then what is the value of this? It's going to be the sum of the rest of the 4. And see, then later on, if other values are given, you can further substitute for GM by R square and everything. Write it quickly, then we have to do certain cases for hollow sphere and everything. That is going to come in your exam. So please write down this class. Everybody, please open the cameras, class. See class, gravitational field for different objects like sphere. Please rest of you open the camera. Abir, Ali, Jobita, Jesleen. Gravitational field. So you have a hollow sphere. Now radius is r. Now we are taking 3 points. This point P is outside. This point is exactly at the surface where I have marked this arrow. And one point is inside. Inside means anywhere like this. See this point that I have marked. So these derivations are not there in your syllabus. It's just that you have to use these formula in the numericals and numericals will be given. So if you have a point outside, okay, for a point outside class, what you are going to do, whatever is the separation from that point, that you have to write it. Okay. Like if you have the separation of the point, let's say 5 meters, whether the radius is 1 meter, 2 meters or anything, that 5 meters you are going to put in there. Means whatever is this separation, this actual distance from the outside part, you have to put there. That's the difference. Easy. And same thing. See, at the surface, from the center, the separation is the radius. So at the surface, you are going to put the radius. Because technically, it's the value of r, as I have discussed, small r becomes equal to capital R. Remember, we have done a graph also when we were doing variation due to acceleration due to gravity. And inside anywhere inside for a hollow sphere, because no mass is present, so no gravitational field is exerted for a hollow sphere, so directly it is 0. Okay, so graph also comes for this. So how do you plot the graph? Again, these points, small r is equal to capital R, gives you the reference of the surface, right? See, if you have a sphere, this is the center, means r is equal to 0, nothing is there. So this is your center origin. And this is the radius, means this is the surface, right? This is the surface. So separation from the center to the surface, small r is equal to capital R, right? At the surface. Now, anywhere in between this point, anywhere we take, means small r is less than capital R, means the radius is greater. And any point we are taking where the small r is less, like these points, small r, small r, small r, that is inside part. And anywhere outside the sphere, that is outside, means this now capital R is greater than the radius. Radius is left here. So it's 0, nothing is there inside. At the surface, you have a value gm by r square, and then it decreases gm by small r square. It is inversely proportional, it decreases. Okay, Ali, no issue if you're outside. Write it for the hollow one, then I'll discuss for the solid sphere. Ma'am, done. See, for solid sphere, just the difference that will arise is in the part of inside one. It is gm into small r, means whatever is the separation that you have taken, means this part, this small r divided by capital R cube. Okay, this is for the solid sphere. Now for the ring, on the axis of a ring means, see, this is in which axis? When you have this circle, this is your x, y axis. And when you have this y and z like this, so this becomes your yz plane. So whenever you have yz plane, you will see the circle aligned like this. And if you will see it from the front, then it will look like this, which is the xy plane. So see, from the center of a circle, when you are calculating, I'll show you. Like this, see, this is the axis that we use in the moment of inertia also we have been using. So if I invert it like this, means if I rotate it by 90 degrees and I look at the from the YZ view, so from the YZ view, see, this will be horizontal. So this is basically the axis which I am referring to, point P, and this separation is R, and this is the radius, capital R, of the ring. And ring has a mass m. So the formula on the axis of the ring is going to be G, capital G, mass of the ring. Small r means the axis, divided by capital R square plus small r square to the power 3 by 2. Now see class, for the center of the ring, if you are calculating at the center of the ring, you know it is 0 because it's a symmetrical figure circle. You can check it from this formula also. As soon as you make the r as 0, see, if you are reducing this to 0, means at the center, this r is equal to 0, where I is equal to 0 means at the center. This is the center. So that time I is equal to 0. Okay, write it till here first. See, gravitational field for a point mass. This we have discussed some portion when we were discussing the strength. So same thing here, when you have the source mass, you have the test mass. So you'll perform the same procedure. I is equal to G capital M small m by R square. So, and per unit mass it is. So one mass will be cancelled. So you have the same formula for gravitational field and gravitational field intensity. Okay, that and the direction is towards the source mass. See, the direction is towards the source mass. Okay, class, because the source mass is producing the gravitational field. Source mass is producing the gravitational field. Okay, and this is further, which is, that's why this is kept as static. So this source mass will be producing the gravitational field, and that's why it is kept as static. Write this, then we'll start with the derivation of the gravitational energy. Okay, Jobita. Fine.
Thank you.
See, class, when we are talking about the gravitational energy, so here in the gravitational energy, whenever you have any sort of energy which is related to force, it is your potential energy, class. So even if I'm using the term gravitational energy, this is signifying the potential energy. Now, class, one method which is directly linked with the potential energy is the work done. Okay. Now, suppose this is Earth, mass is m, and here at infinity we have the test mass which is present. Okay, now at the infinity this test mass is present, and two random points I have taken in between the path till the surface of Earth. These are just two random points which I have taken, and the separation between these two is dx. This is how exactly you have to perform the derivation, class. So whatever doubts you are getting, whatever doubts you're facing, please clarify it step by step. Okay, because it is actually easy. Once we'll do the calculation part, you will find it easy, but it's just that this diagram and everything, this can look a little confusing. What are we doing? See, whenever we have potential energy is basically the, we have done this also in work energy and power when we were doing potential energy. That time we had discussed it. So what is potential energy? It's basically the work done when a particle moves from infinity to a particular point. That is your potential energy. So here what we are going to do, in between 2 points we have chosen, that is A and B point, in between these this whole path. And the separation is dx, means this is a very, very, very small point that I have taken, very small point. Okay. Dx, whenever dx is there, this should be clear to you that you are referring to a very infinitesimally small point. Now from this point to the center of Earth is the separation x. And let's say this is a random point P, okay, at which we are bringing. So this x we have just taken to see to show the separation of a point from the center of Earth, so that we can apply dx. But our point of calculation is let's say P. From infinity, we are bringing it to P point. So firstly, class, when you are performing work done from infinity to P point, it is actually potential energy at P. That's what I'm trying to tell you. Whenever you have the question for potential energy, work done always gets converted to the change in potential energy. This should be the key step for the solving of questions for you. Now, when we are calculating the force, the gravitational force, this is small m, this is the capital M mass, okay? And let's say I have brought the particle to this A point because this is the nearest point, so I have brought it here. So when we are calculating the force, it will be capital G, capital M, small m. And see, right now I'm talking about the point mass M, which is the initial part. We have not actually brought it to some other point. So this is x square. What is this? This is the gravitational force at A point. Right, class? This is at A point. A point, this is the separation is x. Capital G, capital M, small m divided by x squared. Now, when you're calculating the work done in between these 2 points, A to B point, force into displacement, this has to be the standard formula which you use for the work done. Anywhere, this was not just for work, energy, and power. Anywhere, wherever you are using the concept of work done, and if any other formula is not present, like your straight away formula, for you have the formulas like potential energy of a spring, the best example is you use the formula half kx squared. Even after that, you require somewhere to use this. So firstly, see f dx, this is going to be cos 0 degree. All are parallel, we can see. So this is simply f px. So what is the work done that we should put? See, force, what is the force? G, capital M, small m by x square. Displacement is already dx from A to B point. And we are actually integrating. See, if I know from A to B point, class, can I expand it and find it till P point, which is a random point? Do you agree with this? Yes or no?
Yes, ma'am.
Okay. So because this is for a small point that I have taken, and if I know anything, any detail about A to B, I can expand it from anywhere. Let's say we want to find it for P point. Why I have chosen this P point at such a random location is that so that we can form a generalized case. If I write it at the surface, if I write it inside, so it will be very particular for you. You will know that, yes, if it is at the surface, I have to use the formula. Let's take a very difficult and a general case where the point is here. So till from where to where we have to expand this A to B? From infinity. Actually, if we know the information about this, we have to expand it to this point P. So what's the separation of P from the center? R, we had already taken. So it is infinity to R. Class, after this, everything is easy. Just tell me, till here, anybody has any doubt? Clear?
Ma'am, why are?
Because P point is separate. We always take, I have told you, no, in gravitation, we always take everything from the center of Earth, because gravitational force and everything will act from the core of Earth only. So you're not going to take the separation from infinity to the point. Gravitational force is being exerted from the surface of Earth. Even when we were considering A point, when the point mass M landed from infinity to A point, we had chosen X, which was the separation from the center. So in gravitation chapter, everything you have to take it from the center of Earth, or if any other planet is involved. Though you will not be having other planets' whole cases, you will be getting Earth's cases only. And if other planets are present, then you have to calculate the gravitational force that can come. So it's clear, Abir?
Yes, ma'am, it's clear.
And Jesleen and Ali, are you getting this? I hope Ali,
Yes,
you're out.
ma'am.
You're understanding.
Yes, ma'am.
Okay. And it's clear to Jesleen too. Okay. Now see, we have to integrate this basically. So G, capital M, small m, all these are constant. These are taken outside. X square is taken in the numerator. It is x to the power minus 2 and dx integral from infinity to r. So this integration, all of you by now must know how to calculate. See, this is a constant term. X to the power minus 2 is here. N plus 1. This is n plus 1. N plus 1 comes in the denominator. And the limits infinity to r. Okay, class. Now see. What do we have? G, capital M, small m by. This is 1 minus 2, which is minus 1. And this is also x to the power minus 1 from infinity to r. So one thing we can do, see class, if you have x to the power minus 1, so we can bring it in the denominator. So the power will change. So if it is, see, under every number, under every variable, you have 1 hidden as the denominator. If it is written 3, 3 means 3 by 1. 4 means 4 by 1. X means x by 1. So if I have x to the power minus 1, it means 1 is there in the denominator. And you know, whenever you interchange the numerator and denominator, the signs reverse. So this will be 1 by x to the power 1. It means I can write this as G, capital M, small m. And see, minus 1 is in the denominator also. No, I'm writing this as minus. You know, this minus can be written upwards because this is 1. It's like you're multiplying it with minus 1 by minus 1. And here you have 1 by x, integrating it from infinity to r. Let's put the upper limit and the lower limit now. Okay, this step is solved. Now we have integrated it. We just want to put up the upper limit and the lower limit. I hope you know why this is written. If you have anything, let's say x by minus 1, if you multiply and divide it by minus 1, this term will be 1 and this will be minus x. So that's why I've written this as minus. Capital G, capital M into small m. This is 1 by r minus 1 by infinity. Upper limit first minus lower limit. Okay, class. What is 1 by infinity, class?
0.
0, right. Correct, Abhi. This will be 0. So straight away we have the derivation completed. We have the formula of work done as minus G, capital M, small m means M1, M2. This basically represents M1, M2. Why capital M and small m have been taken in the formula? Because this is representing the mass of Earth, and mass of Earth will be there in your formula. That's why this is written in the derivation, because we were talking about Earth only. But see, this is general. You know, it's like M1 and M2. It is acting like M1 and M2. If you have two masses, take them. But usually you will have the Earth present. Even if it is not present, you can calculate. But this is work done. What about the potential energy? As we have discussed in work energy and power also, and everywhere also, that work done always gets stored in the form of potential energy. So this work done is exactly the form of potential energy. So what is the formula? Minus, this minus sign has a significance. Minus capital G, capital M into small m divided by R. Capital G is your universal gravitational constant, whose value is 6.67 into 10 to the power minus 11 Newton meter square per kg square. So this value has to be remembered by all of you. I think in the initial part, we have written it also, so I need not write it again. And what is the significance of this negative sign? Basically, the significance of the negative sign tells you the system is bounded. Whenever you have the potential energy negative, it's a good thing. Means whenever you have potential energy, it can either be positive, it can be negative. Now, when you have positive energy, it means system is unbounded, unstable, minimum potential energy. So when we are referring here, this is minus and this is showing the negative sign. This negative sign, what it is representing? The forces are Just a second. This is showing the forces are attractive in nature, means your system is bounded, your system is stable. And that is what is important whenever we have the case of potential energy. Positive, if you have your U as positive, means it is unbounded. Write it till here, otherwise things will be mixed up. Write it, the derivation, and this derivation is very, very important, class. It's very easy, but it is very important. Please write it and mark it as important. Okay, class, if you've completed, you can leave. We'll continue this tomorrow. Thank you so much.